Hello everyone and welcome to another video of Mathematics for Computer Science and Artificial Intelligence. Today we continue our video with Applied Derivatives 3. So in this video we will discuss multi-regression. Now we have already discussed linear regression and they are very similar, so this video should be a shorter one because we don't have to revisit many of the things that we already learned in the linear regression series. So if you haven't seen that video, just make sure that you go ahead and watch that video before you continue in this one. So the first thing we need to know is what in the world is a multi-regression? And you can think of a multi-regression as something that's similar to a linear regression but with multiple input variables, and thus it has multiple slopes. So this no longer is a line. We will visualize a linear regression at least in 3 dimensions later on. So let's have a problem statement just as we did in the linear regression video, and let's see what we need to solve in this video. Great. So let's see, it says we have collected 15 months of data for a startup company that we are thinking of investing on. We have collected 3 variables in those 15 months. 2 that are affecting the market value of the company, and those are its reputation and innovation, and the market value itself. So we have 3 variables: reputation level, innovation level, and market value. Additionally, we have made projections on what the reputation and innovation will be on the 27th month, meaning 1 year after today. So, based on what the company is going to the market with within the next year. So these are pretty much business projections that we are making based on what products or what services they're going to be offering. This is just an estimation, and thus the market value, even though we're going to solve it, it's also going to be a slightly speculative, let's say. So the problem is that we don't know exactly how the reputation and innovation of the company are affecting its market value. Our goal here as computer scientists is to program a multi-regression to see how much money we will make if we buy 35% of the company, sell after 1 year, and obviously that's also considering that our projections become true. Great, so our job as computer scientists is to find a model of a multi-regression that can fit this reputation and innovation levels and produce a market price or a market value for the company. So let's move on. So this is our data set. Our data set consists of innovation, reputation, and the market value. We also have collected the month in which these innovation reputation levels were gathered. So we collected data from the first month to the 15th month. So this innovation and reputation level are just pretty much floating point numbers, and then the market value is pretty self-explanatory, right? So our projections say that the innovation level and the reputation level would be 3.0 and 0.35 respectively for 12 months after the 15th month, meaning on the 27th month. Now let me just clarify something here. The month itself does not play a role in the actual market value. This is just to, well, actually, let me show you the graph. So here we are graphing in terms of the time. So on the x coordinate we have months, and on the y coordinate we have the market value. As you can see, this is obviously not a line because the month in which the data was collected itself does not really affect the market value. What affects the market value is the innovation and the reputation. This is just for informational purposes only. Now that we have that, we have to ask ourselves, how are we going to program a multi-regression that can pretty much predict a market value for a given innovation and reputation level? So let's remember something from our linear regression. The equation of a linear regression is y equals mx plus b, or we could also say f of x equals mx plus b, right? That's a line. Now, a multi-regression, you can think of a multi-regression as a line of multiple inputs. So the input here is just one, which is x, right? Obviously, f of x, we have one input. For a multi-regression, we have multiple inputs, which we can call x sub 0, x sub 1, all the way through x sub n, or the nth x. Now, these individual m's have a different slope, obviously, because if it was the same slope, well, it could be the same slope. It could be the same number conceptually, but it should be a different one. It cannot be the same. It doesn't necessarily have to mean that they have the same weight. And now that I mentioned weight, by the way, this is multiple inputs and slopes, not a line. Now that I say weights, it's better to visualize this as weights instead of the actual m value. And this is still the slope for each input pretty much. But we call them weight because if you think about it, when you have one input, the weight is the number that tells how much the input matters to the output. So if you have a weight of 0, then that means that this output doesn't really matter at all because 0 times anything is just 0. If we have a slope, a very high slope for, or a very high weight for W1, then that means that the input of x sub 1 matters a lot because the value of x sub 1 will be greatly increased by this high multiplication, right? By this high product. So we go all the way to weight sub n, or the nth weight, and the nth x. And we also have our b value here. Our b value. Great, so let's go into a little visualization before we move on to anything else. Okay guys, so I have this cool tool that I found online. This is GeoGebra. I'm just gonna put a it's like a multiple input function. So let me call it f of x, y. It's in 3 dimensions. And let me just give it a weight of 3x and then a weight for y. Let me just say 3.5 or 2.5 y. And then for b, let's just say it's going to be 0.50. So, as we can see, this is no longer a line anymore. This is more like a plane itself. And if you think about it, in a linear regression, which is 2 dimensions, we have a line, which is like looking at this from this angle, right? So it would just kind of be like a line. However, when we add 3rd dimension, then it becomes a plane. This plane. If we added a 4th dimension, it would become a 4th dimensional plane, or a 5th dimensional plane with 5 dimensions, and so on and so forth. So this is just for visualization purposes so that you know what's really going on. So since we graphed it before in terms of the months, it looked more like a curvy graph. But that curve, it doesn't necessarily mean that it will be a curve. It just has different slopes. And obviously I'm just graphing in terms of time, which could mean any value. It could mean any innovation, any reputation. So even though in 2 dimensions it looks kind of like a curve, in 3 dimensions it's just simply a plane. Great, so let's move back onto our slides. Right, so now that we're back in our slides, let's see. We have a multi-regression already, or let's say a function of multiple inputs and multiple weights. What do we define as the cost? And actually, this is very simple. The cost is still the same as we had with a linear regression because we're still comparing 2 single points. So this produces 1 point, right? Same as mx plus b, except that we have many more inputs. So this produces 1 number, and that number represents the point for the inputs x sub 0 all the way through x sub n. And y for these values of x represents the other point, or the output, right? So the cost is defined as the same thing that we did before. It's just the prediction of our model minus the actual value squared. So this prediction is just this whole thing right here. So we can just visualize it that way, right? It's just this whole thing right here. This is the prediction. And the y is the actual value. So you want to find out the distance between them and then square them, because you just want to find out how far off that particular point is from the actual value. Of course, this is the cost for one row of data. To find the total cost, again, it's the same thing as in the linear regression. You just add up all the costs for all the points in your samples, right? This is the total cost. Great. So sometimes it's a lot easier to visualize this in a different way. So let's see. How many operations we have here? We have 1, 2, all the way through n. So we have n operations plus 1. N plus 1 additions here. And of course we have the multiplication thing going on, but let's just forget about that one. We have n plus 1 addition. Is there a way to actually simplify this? And if you guys have your linear algebra fresh and you remember the dot product, you could actually represent this part right here, this weights times the heights, as the dot product between two matrices. So the matrix that contains all the weights and the matrix that contains all the inputs of x. So once again, this dot product, remember that it's just this times this plus this times this plus all of the other ones plus this times this, which is equivalent to this, right? And then just add whatever number at the end, because this is just a number, right? Right, so this is still the multiple input and slope of a line. This is still the prediction. It's also very useful to have it in this way, because now instead of having n plus 1 additions, we have just one dot product and then one addition. So that's just two operations when you look at it in this way. The cost can also be defined as a dot product, right? Because this is the prediction, and you know that the prediction is this right here. So let's just take this, subtract y from it, and square it. And this is the cost for one row of data. Okay, so we have our cost. Again, I'm leaving it expressed as this, the cost for 1 point, but we can express it as a dot product. Now, the cool thing is that we have to now differentiate this function with respect to b. But look at this. We have to differentiate this function with respect to all the weights that we have. Before, we only had m and b. Now we have b and we have n weights. How are we going to differentiate all these weights, right? And let's see. Let's start with something simple. Let's start with differentiating for b, because this is simple. We have done this before. When we differentiate with respect to b, everything else becomes a constant. So the derivative of all of this inside this parenthesis is just 1, right? Derivative of the cost with respect to b, when the cost is b, is just 1. And then you take the derivative of the whole thing as per the chain product, multiply it, and then you end up with this, right? Not too crazy, right? So this is still just a prediction minus y times 2. This is the derivative of the cost with respect to b for one row of data. Now the challenge becomes, we have the weights. How many times do we have to differentiate this function? And remember that generalization is the best friend of mathematicians and computer scientists. Why should we take the derivative for each of the n's, or the cost for with respect to each of the n's, when we can just take the derivative of one of them, and then let's say we take the derivative of the cost function with respect to the nth weight. N could be any number. N could be 0, which means that it's the derivative with respect to this weight. N could be 1, which means it's the derivative with respect to this weight. Now let's see, what happens when we take the derivative of the cost function with respect to the nth weight? Well, if we were to take the derivative of the function with respect to the 0th weight, we would end up with the derivative of this whole thing. Remember, everything else becomes a constant, so all of this will become 0. So you have the derivative of this with respect to the 0th weight plus 0. So it's just this, right? And the derivative of this with respect to the 0th weight is just x0i. Okay, let's see. Let's take the derivative of this one now, the first weight, or the 1th weight. Take the derivative of this function, everything else becomes 0, and then again our derivative, or the derivative of the inside, is just x1i, which means that if we take the derivative of this, of the nth weight, we end up with just x and I. Great, because n could be anything. So we can just simply say that the derivative of the cost with respect to the nth weight is just 2 times at the nth x for the ith sample times the whole thing, right? We're using the chain rule to actually take the derivative of this whole thing. It's just the derivative of this as if it were one variable times the derivative of the inner parenthesis, right? The derivative of the inner parenthesis is just x and I, and the derivative of the other thing is 2 times this, right? So this is all we end up with, and this is the derivative of the cost with respect to the nth weight for one row of data. And it's actually very simple, that's all it is. Now, of course, we can express these as dot products. So this is the derivative of the cost with respect to B, and this is the derivative of the cost with respect to the nth weight. Again, we will see why this is so important as we start programming this in our next video. Now we also have to define how do we update B and how do we update the nth weight. And this is actually the exact same thing as we did with the linear regression. So let's see. The nth weight will be the nth weight, right? The new value for the nth weight equals the old value for the nth weight minus eta times the differential or the derivative of the total cost with respect to the nth w. Now, let me just clarify something because I'm using eta now. If you come from our linear regression video, you'll remember that we used mu here, which is the other Greek letter. This is also another Greek letter, and this one is more common for computer scientists and actually for this type of model. So we're going to stick to it. So it's just eta, not mu, but it's the same thing. It's just a fraction, a very small number, a number between 0 and 1, that pretty much from this cost, it gets a fraction of it. So update the nth weight, and this is for B. B is just one variable and stays the same thing. So the new B equals the old B minus a fraction of the cost of the derivative of the cost with respect to B. And of course, this is just a reminder that eta equals mu. So it's the same thing. This is also our learning rate, and that's pretty much it. So guys, this is all for this video. Now that we have this part, we can go ahead and code our multi-regression, and this is the training part. So we'll go ahead and do that in our next video, in the computer science and artificial intelligence video, where we deal with multi-regression, and we'll actually go ahead and program one in Python. So I will see you there. Before I leave, I just want to leave you with this thought again. So be curious. Ask questions. Go ahead if there's something that you don't understand, ask yourself questions, ask other people questions, be curious as to why it works. Try to do your own manual work, because that's really the only way that you're going to learn this. And of course, try something out. If you think you have stumbled onto something that you haven't seen before, try it out. Maybe you have. Once again, if you have any comments, any thoughts, any ideas, any questions, please just click the comment down below or just comment down below. If you like this video, please like this video, and also please subscribe if you'd like to see more in the future. Once again, my name is Brian, and I will see you in the next video.